All right, here we are on activity 3 for today. So it's the last activity in the lesson. And it's connecting this idea of how something might change and how it might look on a graph with a real world example. So we're talking about a van that a business bought for $40,000 in 2008. And then the van depreciates. That means it loses its value by 15%. It depreciates by 15% every year after its purchase. So if it's depreciating by 15%, then that means that the van's value is equal to its full value minus 15%, right? And then to have that as a decay factor, we're going to divide by 100 and make it a decimal. So this is 85, and 85 divided by 100 is 0.85. Okay, so we're going to have to make a decision on which graph correctly represents the value of the van. So we're going to be looking for two things. We're going to be looking for an initial amount of $40,000, and we'll see that in the y-intercept. And then we're going to have to use some points and figure out which one correctly shows the 0.85 decay factor. All right, so I do notice that graph A and B and C all start at 40,000, but graph D starts at 30,000. So I know right away it can't be graph D. Okay, I also notice that A is increasing, but we have exponential decay in this situation, so it can't be A. Okay, so it's not A, it's not D, it's going to be one of these two. They both have the correct initial amount, and then we have to determine which one is using a decay factor of 0.85. And so to do that, we can use the information given after 1 year. Remember that you can take sequential points and divide a point value by the one before it to get that factor. And so we want it to be 0.85. So 34,000 divided by 40,000 is 0.85. So graph B would be the correct one. And just, just to find out what it is, what is it if it's 20,000? Oh, it's 0.5. So not the right factor there. So it's also not C. It is definitely graph B. Okay, so graph B shows the correct initial amount of 40,000, and it also shows a decay factor of 0.85, because if the value depreciates by 15% each year, that means 85% of its value still remains. Okay, so to answer the next couple of questions, I might want to write an equation. It says, find the value of the van 8 years after its purchase and show your reasoning. Okay, so 8 years after its purchase is going to be, if I use function notation, the value after 8 years. And so the purchase price or initial value times the decay factor, it's depreciating by 15% for 8 years. Okay. And I could multiply by 0.85 8 times, so it's much more efficient to use an exponent. And we get about 10,000, I'm just going to round that, $10,900. Okay, and number 3, in the same year, which was 2008, the business bought a second van that cost $10,000 less than the first van. So 10,000 less means that it cost $30,000. And it depreciates at 10% per year. So if it depreciates at 10% per year, that means 90% of its value is remaining. Would the second van be worth more or less than the first van 8 years after the purchase? So here's the first van 8 years after the purchase, $10,900. And then we can figure it out for the second one. So the second one was purchased for $30,000 and it depreciates at 10% per year and then 8 years. All right, so 30,000 times 0.9 to the eighth, $12,914 and some cents. Okay, so since that's more than 10,900, the second van would be worth more. More than the first van after 8 years. And then on the same coordinate plane as the graph you chose in the first question, sketch a graph that shows the value of the second van in dollars as a function of years since its purchase. I'm going to go back to where that graph is and zoom in a little bit on that graph. All right, that looks, trying to get it straight in the window there. Okay, that looks good. All right, so I'm going to call this van 2. Remember, it was purchased for $30,000. Okay, so it's going to start right here. And then we're multiplying by 0.9 every year. I'm going to use T for time in years. Okay, so I'll just kind of put the calculator here, find some numbers, and then plot them on the graph. Okay, so let's see here. I can't get it to zoom out. Okay, so let's say we start with year 1. We need to find that point. So 30,000 times 0.9 to the first is 27,000. So year 1, 27,000, obviously just kind of estimating the point. And then year 2, I can do this to the second. And that's 24,300. So not quite halfway up that. And then I'm just going to multiply by 0.9 to get year 3, right? Because that's what changing an exponent would do. 21,870 for year 3. We need to switch. So year 3, 21,870, about there. And then times 0.9 again, 19,683, so almost 20,000. And then 17,714. Okay, so this would be 10, 15. They're probably really close to touching right there. And then, oops, not divide, times. Get the last one. And that's 15,900. So I think it just barely goes above the other value graph at that point. So it almost looks linear because it's kind of spread out growth. Well, this is scaled so much. All right, but for your entertainment, I will put both functions on my graphing calculator. So the first function is going to be 40,000 times 0.85 to the x. And the second one is 30,000 times 0.90 to the x. And I'm going to change my window so it looks like the window on here. It goes from 0 to 80,000. So I'm going to say the x goes from 0 to 6, so 0 to 6. Counting by ones, the y goes from 0 to 80,000. Counting by 10,000. And let's take a look. This is the first van. Okay, and then this is the second van. And they kind of like start to look like they're at the same spot down here at the end. All right, so I think our graph looks pretty good. So that's the end of the lesson. You do have an assignment. It's the practice problems from this lesson, and I will see you next week.